Okay, this is a review video for graphs, graph theory, part 1. It's LO4 part 1. So when we talk about graphs, we talk about vertices and edges. Vertices are the nodes, these dot places, and the edges are the lines of connection. And we use diagrams like this for any description of things that are being connected. This is airplane routes from city to city. The cities would be the vertices, and the edges would be the actual routes. Or we can talk about, computer networking connections or telephone connections. Anytime you have things being connected, we can visualize them with these graphs. So when we look at graph A, vertices, it looks to me, we can count them. Vertices are these nodes. So 1, 2, 3, 4, 5, 6 vertices. The number of edges, let's 1, 2, 3, 4, 5, 6, also 6, and the degree of each vertex. So we can say the degree of A, for example, is how many connections, how many lines, how many edges are going into A. That would be 2. The degree of B, how many connections are going into B? That's 4. The degree of C, just one connection going into it. The degree of D is 0. The degree of E, let's look, it looks like there's 2 connections. And finally, the degree of F is 1, 2, 3. Okay, when they ask about isolated and pendant vertexes, pendant, you can think of, I always draw like a picture of a necklace with something hanging down. That's a pendant. So basically a pendant vertex is when there is only, the degree is 1. There's only one connection point going into or out of it. So this would be a pendant vertex. And then an isolated vertex is when the degree is 0. It's not connected to anything. So D would be an isolated vertex. Okay, let's look at this next example. It's a little more complicated. The number of vertices is 1, 2, 3, 4, 5. The number of edges, let's be careful. It seems like there's quite a few. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 edges. Then the degrees. Okay, so for A, it's how many lines of connection are going into or out of. So be careful with the loop. That actually counts twice. So that's 1, 2, 3, 4, 5, 6. So the degree of A is 6. The degree of B, 1, 2, 3, 4, 5, 6. The degree of C, and again, be careful of the loop. We've got 1, 2, 3, 4, 5. The degree of D, 1, 2, 3, 4, 5. The degree of E, 1, 2, 3. And there is no F in this one. We can erase that one. And in this case, there's no pendant vertex. There's nothing with degree of 1. And there's no isolated vertex, which is something with a degree of 0. Okay, for this question, it's talking about types of graphs. And when they talk about types of graphs, there's specific names based on certain characteristics. So I'll list out all the names and then we'll match them. Okay, the first one is a simple graph. Simple graph means that there is just one line of connection, one edge between each vertex at maximum, and there's no arrows. So this would be what we call a simple graph. Okay, so we did that one. And then A multigraph is when, again, there's no arrows, it's not directed, but you might have multiple lines of connection between different vertices. So that would be this case. This is a multigraph. Okay, now a pseudograph is just like a multigraph. The only difference is you can also have loops, which is a line of connection starting at a vertex and ending at that same vertex. And again, it's still undirected, meaning there's no arrows. So this would be called a pseudograph. Okay, and a simple directed versus a multi-directed. So obviously we can look at D and know it's some kind of directed graph because it has arrows. Now the question is whether is it simple or multi. So simple would mean there's not duplication of routes, of arrows. And multigraph means there might be. So what I see here, in fact, is look for example from C to D. I see two different arrows forming that same connection. Similarly, we've got from B to C a duplication. We've got two different edges going the same direction to the same two vertices. So I would call this a directed multigraph. And it is important that you know the names of the different types of graphs. Okay, now it's asking us about degrees and neighborhoods. We've already talked about degrees, but we'll also now talk about neighborhoods of different vertices. So let me make a little table to answer this question. Okay, let's start by looking at vertex A. The degree means how many edges are going into or out of it. So the degree in this case is 2. And the neighborhood is what are the directly adjacent vertices that connect to A. So the neighborhood in this case would be B and F. Okay, let's look at vertex B. The degree is 1, 2, 3, 4. And the neighborhood would be the things that directly connect to B, the vertices that directly connect to B. So that's A, C, E, and F. You don't have to put them in any particular order, but I like to try to put them in alphabetical order. And let's try C. 1, 2, 3, 4. So the degree is 4. And the neighborhood would be B, D, E, and F. B, D, E, and F. And D. Let's look at D. We've got the neighborhood is, the degree is just 1. The neighborhood is C. That's a pendant vertex. Okay, for E, 1, 2, 3. The degree is 3, and the neighborhood is B, C, F. For F, we've got 1, 2, 3, 4. And the neighborhood is A, B, C, and E. And lastly, G has nothing connecting to it. It's isolated. And so we'd say 0 is the degree, and the neighborhood, there is no neighborhood. All right, I'll let you do the next one. You can pause the video and try to fill out this table. But okay, let's do it together now. So A, the degree of A, 1, 2, 3, 4. The neighborhood of A is B, D, or E. No need to write E twice. It is the neighbor. Okay, and for B, we've got 1, 2, 3, 4, 5. And the neighborhood, it's A. It goes back to itself, B. Oh, sorry, 6, wrong. 6. A, B goes to C, and D, and E. All. B is connected to everything. Okay, we'll look at C. C is just 1, and its neighbor is B. We'll look at D. D is 1, 2, 3, 4, 5. And its neighbors are A, B, and E. Okay, lastly, E. Wow, E looks like a lot. 1, 2, 3, 4, 5, 6. Degree is 6, and its neighbors are A, B, and D. Okay, for this next question, we're talking about the chromatic number. So here's the rule with the chromatic number. We want the smallest number of colors, and the rule is that no two colors can be neighbors. So you can't have a red vertex next to a red vertex, for example. So here's the strategy. You pick a color. I always pick red. It's my favorite. And then look at the neighbors of that first vertex. So I see the neighbors are B, G, and F. And they cannot be red. Okay, so I'll pick another color for B. That's fine. Now I'll move to G. Now G is connected to both B and A. And so it cannot be red, it cannot be purple. So I'll have to pick another color. Okay, now I look at F. F is connected to the red and the yellow. So in fact, I don't need a new color. I can stick with purple because again, we're trying to minimize colors. So only choose a new color if you must. All right, let's look at C. So C is right there, and it's right now next to purple and yellow, which I cannot have it be purple or yellow, but I could choose red. Again, you don't want to take a new color unless you absolutely have to. All right, let's look at E. E could be either red or purple, doesn't really matter. So I'll make it red. It's not touching any red, so that's fine. And in which case, I can make D purple. Therefore, the maximum number of colors I needed to complete all of this is 3 colors. And how is this useful? This is useful for task scheduling. So imagine the vertices that are next to each other are tasks that you can't do at the same time. So each, like maybe it's the same person, you know, having to do each of those tasks if they're connected by this edge. And so basically each color would represent a time slot when those things can get accomplished. So that's the application is often to do with scheduling when you have conflicts. Okay, anyway, the chromatic number in this case is 3. All right, now we're going to move on and we're going to talk about an adjacency matrix. Adjacent, remember, adjacent means next to or in the neighborhood of. So when we talk about an adjacency matrix, we're talking about the vertices. There's A, B, C, and D. An adjacency matrix, by the way, is always going to be square. And when I say square, it means the same number of rows and columns. So the same number of rows is going to be the same number of columns, which is equal to the number of vertices. So in this particular case, we'll have rows labeled A, B, C, and D, and we'll have columns labeled A, B, C, and D. So the question we ask ourselves, for example, for that space in the matrix is how many edges, how many connections are going from A to A? So there's no loop there, so in this case we say 0. How many connections are going from A to B? 3. How many connections are going from A to C? 0. How many connections are going from A to D? 2 connections, 2 edges. Okay, let's look at B. How many connections are going from B back to A? Also 3. How many connections are going from B to B? There's no loop at all, so none. How many connections are going from B to C? Just 1. And from B to D, also just 1. Okay, for vertex C, how many edges are going from C to A? 0. How many connections are going from C to B? Just 1. How many connections are going from C back to C? In this case, we do have 1. And how many connections are going from C to D? That would be 2. And lastly, for D, how many connections are going from D to A? That's 2. How many connections are going from D to B? That's 1. D back to itself is 0. And D back to C is... Oh, sorry, I made a mistake. Sorry. D to C is 2. And D back to itself, there's no loop. That would be 0. Okay, now we are going to do something similar, but it's called an incidence matrix. And this is relating the vertices, these vertices, and the edges. So in this case, the vertices become the rows. We've got V1, V2, V3, V4, and V5. And the edges become the columns. So I've got E1 through E8. And for each different graph, there's no relationship between the number of vertices and the number of edges. You can have the same number, you can have more vertices and fewer edges, you can have more edges and fewer vertices. It's just different for each graph. Okay, so in this case, you look at V1, vertex 1, and you see what edges is it touching. It's touching E1, E2, and E3. E1, E2, E3, it's not touching the other edges. Okay, we'll do the same for V2. It's touching E2, E3, E4, E6, E7. E2, E3, E4, E6, E7. The other ones, it's not touching at all. Okay, we'll look at V3, just E4 and E5. And the other ones, it's not touching at all. Okay, and V4 is touching E7 and E8. So the rest get zeros. And lastly, V5 is touching just E5 and E6. Okay, so this would be the incidence matrix for this pseudograph. It's a pseudograph because it's undirected and it has loops and multiple paths between some of the vertices. Okay, this question has many parts, so we'll do one part at a time. Where they're saying, look at this connection. Start at A, go to E, go to B, go to C, and then go back to B. Is it a path? Yes. Is it a circuit? No. A circuit is when you start and end at the same vertex, so no. If it's a path or a circuit, is it simple? In this case, simple means you don't repeat, you don't go back on the same edge. So in this case, no, it's not simple because we go from B to C and then from C back to B. If it's a path or circuit, what is its length? Its length is the number of edges. 1, 2, 3, 4. Okay, let's move on. I'm going to clear this and we'll move on to the next one, number 2. Okay, now we'll look at the next one. Start at A, go to E, back to A, and then to D, and then to B, and then to C. And problem is we can't go to A there. That's a problem. So is it a path? No. So since it's not a path, the rest we can't answer because you cannot go from C to A. There's no connection there. Okay, let's look at the third one. Starting at E, E to B to A. Again, that's a problem. You can't go from B to A, and so we'd say no, it's not a possible path, in which case we don't answer the rest of those questions. Let's look here. We've got C to B to D to A to E to C. Is it a path? Yes. Is it a circuit? In this case, it does start and end with the same vertex. So yes, it is a circuit. Is the path or circuit simple? We did not repeat any of the edges, so yes, it is simple. And what is its length? So the question is, how many edges did we use to get from start to finish? So we went C to B. 1, 2, 3, 4, 5. The path length is 5. Okay, now this last question is a very common application, and you can go on YouTube and find many, many more examples, but I'll do this one. Basically, there is an algorithm, which means a set of steps by which you can find the shortest distance from any one vertex to any other vertex. And you might look at this graph and say, well, I can just see it with my eyes, which is true. But often in real life, we'll get much more complicated diagrams. So it's very helpful to have sort of a procedure, step by step, how you figure out the shortest path from one place to the next. So I'll walk through Dijkstra's algorithm for us to figure it out. So we start at the first vertex because we're trying to go from A to Z. So we start and we say, look, A, we didn't have any vertex before, and it didn't take us any distance to get there. So that's our starting number. And then the remaining vertices are B, C, D, E, and Z. Okay? So if we're standing on A, we could either go to B in 2 or we could go to C in 3. So from A, we could get to B in 2, and from A, we could get to C in 3. The other vertices we can't get to yet. So what we'll want to do is go the shortest distance. So we'll say, all right, from B, I can get there from A in 2. So I'll pull this over here and I'll bring B and I'll say, look, if I came from A, I'd get there in 2. So now what's left over? Because we've already arrived at B, we've got C, D, E, and Z. Okay, let's look at each vertex one by one. So from B, I cannot get to C. So the only way was what I already knew, was getting there from A, and it took me 3. D, now I can get to. I can get to it from B, and it would be a total of the 2 to get to B, and then 5 more would be 7. So I can get to D from B, and it would take me a total of 7. Okay, I can also get to E from B, and it would take me a total of 2 plus 2, 4. I still can't get to Z yet, so I'll leave that one. And now I'm going to look at these vertices and pick the shortest path. So I'm going to pick C and say, look, we already figured it out. The shortest path is still from A, and it takes me 3. So what's left over is D, E, and Z. So from C, I can't get to D. So still the shortest path is from B, and it was 7. Look at E. Actually, I can get there. Let's see, that would take me 8 to get to E, but I'm not going to do it 8, meaning from here to here. 3 plus 5 is 8. But I'm not going to choose that. Why? Because I know I can already get there using this path of 4. So I'm still going to say, look, coming from B and only taking 4 is better. Now again, remember, I'm standing on C. I still can't get to Z yet, so I'll leave that one. So now I look at my 2 vertices that are left over, and D and E. Which one is shorter? Is E. So we've decided the shortest path to E is from B, and it takes us 4. So if I'm standing on E, what are my choices? I can either go to D, or I can go to Z. And by the way, E, I came from B, so I came this way. So if I went to D, it would take me 2 plus 2 plus 1, 5. That's actually better than my previous route. So I'll say I'm coming from E, and it will only take me 5 to get to D. And then to get to Z now, I can get there coming from E. 2 plus 2 plus 4 is 8. All right, now we look at our two vertices, and we see that going to D in 5 is the shortest route so far of the ones that are left over. So we got there in 5, and so now let's see. Now we knew we could get to Z in 8, but now if we go here, so coming from this direction, A to B, 4, 5, if we add 2 more, that's 7. So that would mean it's better to come from D, and we can get there in 7. So that's how we should get to Z, coming from D, and we got there in 7 moves. That's the shortest path. So let me walk it back. We went to D, and then from D we went to E, and then from E we went to B, and then from B to A. So the shortest path is A to B to E to Z, to D to Z, which is 7. It's a little complicated, but you can practice some more and hopefully get good at it. All right, good luck.